Welcome to the Kinematics of Rigid Body Motion, a discussion based on the fourth chapter of Herbert Goldstein's treatise, Classical Mechanics. Today we are going to go through a brief introduction to the chapter, and then we are going to discuss the independent coordinates of a rigid body. Previously, a rigid body has been defined as a system of mass points subject to the holonomic constraint that the distances between all pairs of points remain constant throughout the motion. And our focus throughout this chapter will be on the general kinematics of rigid body motion. Namely, we will study the nature and characteristics of the motion. We are going to focus a lot on the mathematical techniques for describing rotations, and we will conclude with an analysis of the time rate of change of a vector, and we will look at the dynamics in rotating frames. Now, regarding the independent coordinates of a rigid body, the starting guess is of 6 necessary coordinates. That is, 3 for the position of some reference point and 3 more for the orientation of the rigid body about the given point. A rigid body made of n points will have 3 times n degrees of freedom subject to the constraints listed here. So the distances between any given pair of points in the rigid body has to remain constant. However, these constraints are not all independent, as the number of constraints for n points is the one given here, simply summing up the number of equations. This is much larger than the number of degrees of freedom if the number of points is large. So another way to think about this is to say that in order to fix a point on a rigid body, we first of all require the distances from it to 3 other non-collinear points. So therefore, fixing 3 points will determine all the other points through rigid constraints, and we end up having at most 9 independent degrees of freedom, which are the three pairs of the sets of 3 coordinates for each of these 3 points. But the 3 points themselves are subjected to constraints, which are listed here. So the distances between them have to be fixed. So we end up with a total of just 6 degrees of freedom. Alternatively, we can think about it in this way. Point 1 will require 3 coordinates in order to be fixed. Then point 2 is necessarily located on a sphere centered on point 1, and point 3 is on a circle drawn about the axis joining the first 2 points, which once again implies 6 independent degrees of freedom. This remains true in the limit of a continuous body, and the number of degrees of freedom can be reduced further by additional constraints like a fixed point or movement on a fixed surface. Three coordinates are required to specify the origin of a frame fixed in the rigid body relative to the laboratory. The remaining 3 coordinates specify the orientation of the body set of axes relative to a frame having the same origin but being parallel with the laboratory frame. This last set is specified by the direction cosines. So the 9 direction cosines are the dot products between the primed set of axes and the unprimed set, which is considered to have the same origin as the primed set, but is always parallel with the laboratory frame of reference. And the nine dot products are listed here. And for them, we can of course express the primed axes in terms of the laboratory ones through linear combinations involving the direction cosines defined above. So the 9 direction cosines specify the orientation of the primed set of axes relative to the unprimed or laboratory frame. The radius vector of of any given point will have a set of free components in the laboratory frame, but alternatively we can also write its components primed in the primed coordinate system. And then using the direction cosines, we can express the primed components of the vector in terms of the laboratory components simply by taking the dot product between the radius vector as written in the laboratory frame and uh, each of the given primed axes. And we obtain the linear combinations here involving the laboratory coordinates and the direction cosines. Alternatively, we can express the laboratory components in terms of those in the primed frame by once again taking the dot product, this time between the radius vector as expressed in the primed frame and the axes of the laboratory coordinate system. And we will obtain the linear combinations involving the primed components and the direction cosines. So the direction cosines relate the coordinates of a point into reference frames. And obviously what was true for the radius vector is true for an arbitrary vector. And we can always, for example, write the primed components of the vector in terms of the laboratory components or the other way around. So we have seen that the transformation between two coordinate systems is spelled out by the direction cosines. If the primed axes are fixed in a moving body, the direction cosines will be functions of time as the body changes orientation during its motion. They are the coordinates describing the instantaneous orientation of the body relative to a frame having a common origin with the primed frame but being parallel to the laboratory frame. However, they are not independent coordinates, as they are 9 and only 3 coordinates are required in order to specify an orientation. They are connected by the fact that the basis vectors in both frames are orthonormal. So what we mean by this is that in the laboratory frame, the three versors obey the conditions here, so they are orthogonal to each other and all three are of unit length. And this remains true in the primed set of axes as well, even though the frame itself has a different orientation with respect to the laboratory frame. The unit versors are still orthogonal to each other and they remain of unit length. So now if we expand equation 4.4 into 4.7, we get the following two sets of equations. The first one says that if we sum over products of direction cosines having different indices, we obtain 0, whereas if we sum over squares of direction cosines having a fixed index, we obtain the value 1. And as these are two sets of free equations each, the number of independent degrees of freedom is once again reduced to 3. So out of 9 initial direction cosines, we are reduced to only 3 independent functions of them. Furthermore, by using the standard definition of the Kronecker delta together with the two sets of equations in 3.8, we can contract these two sets to a single condition, which is the one given here, and it is what we will call further the orthogonality condition. The conclusion so far is that a Lagrangian and its equations of motion cannot be set up using the 9 direction cosines as generalized coordinates. Rather, 3 independent functions of the direction cosines are required. However, direction cosines find use in describing the connection between two Cartesian coordinate systems. Many results concerning the motion of a rigid body can be expressed with great elegance and generality in a manner that leads naturally to procedures used in the theory of relativity and in quantum mechanics. Consider now a primed set of coordinates which was obtained by rotating about the laboratory x-axis with an angle theta. And so then we can write the direction cosines of the prime frame in a in a very straightforward manner. They are listed here. Again, by assuming we have obtained a primed frame by rotating about the unprimed x-axis with an angle theta. So the direction cosines are the ones listed here. Then we can rotate again, but this time by an angle psi around the primed z-axis. So this will lead us to a frame which has double prime indices. And once again, the direction cosines of the double prime frame relative to the prime frame are given straightforward by the in a straightforward way by the values here. And since we know since we know this set of direction cosines, it means we can express the primed versors in terms of the laboratory ones, and therefore we can also write the double primed coordinate axes in terms of their projections on the laboratory axes using the the ensuing direction cosines. So simply by expressing the primed axes through the relations here, we can write the direction cosines of the axes having double primes on the laboratory axes. And having these expressions, we can investigate what happens when we rotate the frame about the original z-axis by an angle phi. So our initial situation prior to this rotation is that, for example, the double primed I-axis is written like here in terms of the laboratory frame. So if we now look at for example, its direction cosine with the original I-axis, then we speak of an original angle alpha, let's say, to which we add an additional angle phi from the rotation about the z-axis. So we want the cosine of this new angle, and if we just use the trigonometric identity to expand it, we can then identify the quantities here and here just with these two components. So the end result is the one here. Similarly, we can look at the direction cosine on the j or the y-axis, which is going to be given by the sine of this new angle. So if we once again perform the expansion and use the same identification, we can write the formula here. And lastly, for the direction cosine on the old z-axis, this is straightforward given by the quantity here. Since we rotate about it, the projection here does not change. And you can see that if you square these relations or add them up, the length of the versor having a free prime being triple primed is equal to 1. Similarly, we can write j double prime in the laboratory frame and use the same argument to construct its direction cosines with the old laboratory axes, and we obtain in the exact same way we obtain the quantities here, and we can do the same for the triple primed k-axis. Starting from the double primed axis written in the laboratory frame, we can then write the projections of the rotated axis on the original laboratory coordinates. And we will see later on that this kind of sequence of angles, so these kinds of combinations of angles are in fact identical with a very general parameterization which can be used to describe any rotation. So in summary, we have derived the number of independent coordinates of a rigid body. We have specified the orientation of a rigid body in terms of the direction cosines, and we have derived a general transformation of the coordinates in terms of free rotations and the direction cosines. and in the following we will discuss orthogonal transformations. That being said, I want to thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.